Hey everyone, so we're going to finish up our discussion about rotational energy, and we're going to take it one step further. So in the previous part, we just talked about energy, how to calculate it, how to calculate the work, how to calculate the kinetic energy, and though we did a little bit of conservation of energy, we really want to make sure that we actually see how that works in this type of scenario, in the more complex, if you will, type of questions. Mainly because if you recall, in the energy unit, the concept of conservation of energy was a major part. There was very few times where you were actually finding the kinetic energy by itself or the potential energy by itself. It was always a relationship. So basically, what we really want to focus on is what happens when we have both the rotational and translational types of kinetic energies. I said this before that the most common scenario is basically wheels traveling on the ground. And in particular, I'm going to focus right now on a wheel going down an incline. So, like always, the first thing that we want to do is ask ourselves, how would we do this in the linear case? Well, if we had an object on top of a ramp and it was going down it, and we want to know what its speed was, well, using energy, we know that it's starting at some height, so it's starting with some gravitational potential energy. By the time it reaches the bottom, it ends up with kinetic energy. And we know that because there's no energy being lost to friction, that energy has to be equal. So whatever amount of potential it starts with, it gets that amount of kinetic energy by the time it reaches the bottom. So we're going to end up doing something very similar. We set the potential equals to kinetic and we can solve for V. But this time, the thing that we have to be careful of is that we have two different kinetic energies at the bottom. So not only is it going to have the translational kinetic energy of 1/2 mv squared, but it's now going to have this rotational aspect as well that we have to incorporate. So what ends up being different between the previous case and now is that the amount of potential energy it starts with is now going to be split up between these two types. Some of that potential energy is actually going to be put in towards rotating the wheel, while some of it is being put into moving the wheel. Now, you'll notice that I put a little subscript on the V for cm. This just stands for the center of mass. So this is just referring to the typical speed that the wheel is traveling. And then we have this I omega. So from here, there's a few things that we can do. First, depending on the object, we're going to replace that I with something. So we could replace it with the 1/2 mr squared or just mr squared, depending on whether we have a disk, a hoop, a sphere, whether that sphere is hollow or solid, yada, yada, yada. However, there's something that we have to talk about when it comes to that omega. Now, if you recall, we have a relationship between omega and linear speed. That omega is the linear speed divided by r. Now here's the issue. I can plug in V over R in for omega. But now I end up having two V's. I have a VCM and this V. And the question is, are these the same V? Is the V that I get when I basically multiply omega with R the same VCM that I'm getting, for how far it's traveling? And the answer is it depends. It depends on the question. So when you're reading these questions, you really have to pay attention to the phrasing. First, if the question says that the object is rolling while slipping, or I didn't put this here, but if it says it's frictionless, so like the incline has no friction, that means that the object is going to essentially be sliding, or in this case could be rolling, but not rolling because of the surface, or not directly related to the surface. So it ends up being that the omega that it has, the rotational speed it has while it's falling, isn't the same as what we would get with the VCM. So the main idea here is if the object is slipping while it's rolling, or if it says it's frictionless, which basically means that it'll end up pretty much slipping the whole time, that means that we're not going to want to go through that route of replacing the omega with the V over R. Typically, we would have to do something else in the question to figure out what that omega is before we can keep going. That could be either because they straight up tell us what the omega is, or maybe they give us a little bit of information, like they say as it's rolling while slipping, it completes 10 cycles in 30 seconds, and then we could use that information to figure out what that angular speed is, and then we would plug it into that equation. The other scenario would be if it says that it is rolling while slipping. Now, in this specific case, if it says that it's rolling without slipping, then the omega that we have in that I omega squared is actually related to VCM using our conversion equation. Now, what this means is that if I replace the omega with V over R, it's going to end up being the same V, and in that case, I can actually simplify the equation better. Now, what this allows us to do is basically drop that CM subscript for simplicity's sake, and then we can now see that we have a V squared here and a V squared here, and that can help allow us to basically move forward in our calculations. So just to reiterate, in the two scenarios, the wheel could either be rolling without slipping or rolling while slipping. If it's not slipping, like in this second case, then we do want to replace the omega with V over R, because that's pretty much the only way that we're going to continue solving it. If it says it's rolling while slipping or that it's frictionless, we're not going to want to replace the omega with V over R. We're going to want to find what the value of omega is in some other way. So when you use this equation, regardless of the scenario, we're still going to do UG equals K trans plus K rotational. It's just whether or not we replace the omega with V over R. All right, and that's definitely the key aspect. All right, so here's the first question. Pause the video, it works out. We'll go over in a second. All right, so in this question, we have the ball going up the incline. Even though I gave you the scenario for something going down the incline, it's the same thing. You just flip the initial and final sides. You know, instead of starting with potential and going to kinetic, we're now starting with kinetic, going to potential, but it's the same thing. So we have this, the two kinetics going into potential. I plug in my equations. I replace the I with the 2/5 mr squared. And because it says it's without slipping, I'm going to replace the omega with V over R. I have a mass in all three terms. And on this right-hand side, I have an R squared and an R that's being squared. So I end up getting this. Now, you may notice I did something a little bit weird. You might be wondering, why am I not multiplying the 1/2 by the 2/5? I'll explain that in a second. But one thing I noticed is that both these terms have a 1/2, so I'm going to multiply both sides by 2. And since both of these terms have a v squared, I'm going to factor out that v squared. So I end up with 2gh equals 1 plus 2/5 v squared. I plug my numbers in, and I get my answer as the max height being 10.1 meters. Now, let me go back to why I didn't simplify the 1/2 times 2/5 before. The reason being is because I have enough experience with these types of questions to know that a lot of times there's a follow-through question with these, especially for free response, that we want to keep an eye out for, where they change the ball. So instead of having this sphere, which I believe is the solid sphere, if they change it to be a hollow sphere, well, we know that the 2/5 ends up changing to something else, like a 2/3. Okay, so in that case, what I would do is, instead of having to go through the entire process from the beginning, essentially, and recalculate everything, I could just go to this final step, and before I take advantage of the 2/5, I just replace this with a 3 and make it 2/3, and voila, I can now do one single calculation to finish off my problem. So like I said, this is just something I've gotten used to over experience, but if you don't want to worry about that, feel free to do whatever you need to do. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this is basically the same thing. Again, the other way around. We're going to start with the potential going to the kinetic. Same thing. This time I'm going to do something a little bit different, only because, like I said, there's a part B. As you could probably tell, there is going to be a part B and C. So what I did was I actually replaced the 1/2 with an x. This is actually another thing that I usually do. I like to solve it with this x term because, like I said, I know that when they switch up the material, that the only thing that's changing is that coefficient. So I'll put in a variable coefficient, if you will, and that way I can, do the calculations with it without being tempted to simplify the fractions. So once again, I do the same thing. I have a mass in all three terms. I have an two r squares that I can cancel out. I get this. Multiply both sides by 2, factor out the v squared, and you'll see right off the bat that I already start off with that, end up with that equation that I had last time. 2gh equals 1 plus x all times v squared. So plug my numbers in, solving for the wheel, and I get that the speed of the wheel is 10.3 meters per second. All right. Now, before you work on this, I want you to try to attempt this two different ways. First, I want you to try to solve this conceptually without doing calculations. Think about what exactly would happen to the speed. Would it go up? Would it go down? And why? And try to answer this as if this was an AP question. After that, or if you're having trouble with that, you can feel free to do the calculations, figure out what the actual speed is, but then try to go back and see, A, did it match what your expectations, and also B, if you can actually now use your calculations to explain what's going on. So pause video, work self, and we'll go over it in a second. All right, so part B says, well, how would the speed change if the wheels replaced with a hoop? All right, so this is where we have to kind of really think about what's going on and try to get into the habit of answering these questions, like I said, as if this was an AP test where we have to try to follow a logical set of steps. So we started with a wheel and now we have a hoop. So what changed? Well, what changed is that this 1/2 essentially became a 1. So my inertia increased. All right. Well, what didn't change? Okay, so we're starting with at the same height, so we're starting with the same gravitational potential energy. I'm still going to kinetic energy, kinetic translational plus kinetic rotational, and now I can think about, well, this rotational inertia is increasing, so what's happening over here? Well, the only term that's related to the rotational inertia is this, the rotational kinetic energy. If the rotational inertia increases, that means the object is starting to become harder to rotate. That's what it is, what's happening conceptually. So the amount of energy that's going to be required to rotate it is going to have to go up. If we start with the same gravitational potential energy and the amount of energy required to rotate the object has increased, then that means that the kinetic energy related to it moving is going to have to decrease. So I expect that the speed should go down. And that would be the steps. You would talk about how you started with the same gravitational potential energy. You're still going into the two kinetics. Talk about what's now different, the rotational inertia, because that coefficient changes. With that increase, then we know that the rotational kinetic has to increase, yada, yada, yada. So let's see, does this match our, does the calculation match? Okay, so again, I can start with that 2gh equals 1 plus x v squared. I plug it in, plug a 1 in for x because this is a hoop, and I end up getting 8.94 meters per second. So the hoop is traveling slower, which is exactly what I expected based off of my explanation. Now that the rotational inertia is higher, it requires more energy to be put into rotation in order for it to actually rotate. It's becoming harder to rotate, requiring more energy. All right, now for part C, they replace this wheel with a block. All right, well, I could do the same thing. Well, what's different about the block compared to the wheel? Well, obviously, it doesn't have a rotational inertia. So that means this object isn't actually going to rotate. So now when I look at this, what stays the same and what's going on, well, once again, we start with the same drop from the same height, same mass, so it's same gravitational potential energy. It's still turning into kinetic as it goes down, but now because it has no rotational inertia, it has no rotational kinetic energy. So unlike last time, all the potential energy isn't going to be split between the two kinetics. It's all going into translational kinetic. And since all of the energy goes into translational kinetic, the object is going to travel faster. So I expect the speed should be higher than what I had before, which was about 10. So let's see. I can actually still use this equation, even though this equation was derived and made through the belief that there was a rotational kinetic energy. I could still use it. I just set the coefficient, this fraction, equal to 0. If I do that, that essentially gets rid of the rotational part because the 1 is actually the translational and this is the rotational. So I plug this all in and I'm getting 12.65. So this is essentially the fastest that the object can end up traveling. And again, matches exactly what I said. We have no rotational inertia. We have no rotational kinetic energy. Therefore, all that potential energy we started with, which is the same, is going straight to kinetic. Like I said, the hardest thing for people for this AP is being able to phrase their explanations in a logical way, where you're constantly showing the steps that you took to get to a certain point, where you're showing the equations, you're using equations and these rules and laws, conservation of energy, all this stuff as a way of justifying it. Unfortunately, the AP does not really approve of just doing the calculation, saying, see, that's what happens. You need to get into the habit of being able to explain it in words and not just words of that sort of make sense, but scientific words. All right, there's 2 more, so pause the video, work itself. I'll go over in a second. All right, so once again, we had this question and we're dropping the objects down the ramp. This time we're dropping 5 different objects: a disc, a hoop, a solid sphere, a hollow sphere, and a frictionless block. And we want to know the rankings of their speeds as they get down. So once again, we want to think, what's the difference? Well, all 5 of them have different rotational inertia. Disc has the fraction of 1/2. The hoop has a fraction of 1. The solid sphere should be 2/5. The hollow sphere, if I recall correctly, should be 2/3. And the frictionless block should be 0. So most likely I'm going to rank these in order. Now I need to think about, am I ranking them from lowest to greatest or from greatest to lowest? So let's try to figure out where the block goes, because that one's going to be the easiest. So just like I said before, if we drop a block down the ramp, it's going to start with gravitational potential energy, and then it goes only to translational kinetic. So it's going to go UG only to translational kinetic. However, with the other 4 objects, that same gravitational potential energy is going to be converted into kinetic, translational, plus rotational. So because of this, the block is getting a much greater portion of that starting energy than the other 4 objects. So I know that my fastest should be the block. So through logic, this should be the, which one's smaller? This should be the solid sphere, the disc, the hollow sphere, and then the slowest being the hoop. And that's exactly what we see here. So what I did was I just took the block, the only one that's not rotating, compared it to what would happen for anything that rotates, and used that to figure out whether it was at the fastest or slowest then. And then from there, I could just rank their rotational inertias from then on. All right. Here's the next one. Pause video, work itself. I'm going to go over in a second. All right. So we're going to do the same thing, where we're going to first look at what's going on with the block and compare it to like the rotating objects. So this time they're being shot up the ramp, and we want to compare their max heights. Again, we're going to end up ranking their rotational inertias. The question is in which order. So for the block, we start with translational kinetic energy, and that goes into UG. So far, so good. Works same way as before. Now, for the other four objects, though, they're going to start with K translational plus K rotational going into this gravitational potential energy. Well, unlike last time, where they had the same gravitational potential energy, which was being split between the two kinetics, this time the number that's the same is their kinetic energy. So all five objects, because of the fact that they're starting with the same initial speeds, that means they have to be starting with the same translational kinetic energy. So if this starts with, let's say, 50 joules of kinetic, then we know that the block ends up gaining 50 joules of potential. But for the other four objects, they're going to start with the same 50, but they're going to end up also having some sort of rotational energy also included. So it's going to be 50 plus something else going into gravitational. Because of the fact that the rotating objects are having an occlusion, some extra energy put in, we know that the rotating objects should go higher and the block should be the lowest. So from here, we can rank them again, being the block, then it would be the solid sphere, the disk, the hollow sphere, and then the hoop being the highest. And conceptually, this makes sense. We're ranking them, the more rotational inertia they have, the greater their initial kinetic energy, because they're all traveling with the same speed. They're going to travel with the same rotational speed as well. So the only difference is that I term. The bigger that I term, the more energy they start with in the beginning, the more energy they're going to end up at the end, which means the more height they get. And that's exactly what we see. So once again, you want to make sure that you're using the statements, you're using the equations and the setups, and trying to figure out a way of comparing what happens to rotational inertia to the equation. Think about what exactly is being changed there and how that affects the other stuff. That's pretty much it. Like I said, calculation-wise, this isn't going to be a tough one. What's going to be tough is the conceptual aspect of being able to explain it in words of what's going on. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.